They were looking at a pretty interesting result regarding the closure of a certain class of irrational numbers. So let's see a more careful statement of that situation. So let's say that x is a number of the form square root of a plus 1 plus square root of a, where a is a natural number. Notice that x is pretty clearly irrational here. Then what we'll prove is that any power of x is also of that form. So in other words, it equals the square root of a sub n plus 1 plus the square root of a sub n, where a sub n is a natural number. So in other words, it's the square root of some positive integer plus 1 plus the square root of that positive integer. This kind of form of numbers is closed under exponentiation. Observe that means that we could make a subring of numbers of this form if we wanted to. Okay, so let's maybe do a bit of exploration first, and then we'll see where to go from there. So let's start with x. I'm just going to rewrite x over here. So we've got it. It's square root of a plus 1 plus the square root of a. And I'm going to call this x to the 1, or I'll think about this as x to the 1. So observe, that means that under this setup, our number a sub 1 is equal to a. Now let's look at x squared. So squaring this out here, let's observe that we'll have a plus 1 plus a. In other words, we'll have 2a plus 1, and then we'll add that to 2 times the square root of a squared plus a. That's just by, foiling out x squared, if you will. But we want to maybe rewrite this in the form like this over here, but that's not too hard in this case. Notice that's going to be the square root of, and then we'll simply square 2a plus 1 to put it inside there. But if we square 2a plus 1, we get 4a squared plus 4a plus 1. And then here we'll bring the 2 inside. But bringing the 2 inside the radical means we have to square it. That's going to give us the square root of 4a squared plus 4a. Okay, cool. But now let's observe that we've got a number here, this 4a squared plus 4a, and then we're adding 1 to it, and then we've got that number over here as well. But that means we know the format of our a sub 2. So a sub 2 is now going to be 4 times a squared plus a. I'll factor the 4 out. Okay, so now let's look at x cubed. So cubing x will get the following. So what I'll do here is I'll use binomial expansion. So this is going to be a plus 1 to the 3 halves plus 3 times a plus 1 times the square root of a plus 3 times the square root of a plus 1 times a, and then plus a to the 3 halves. So that's what we get when all is said and done. But then factoring the square root of a plus 1 out, well, we can do that from this term and this term, so the first and the third term. That's going to leave us with what? Well, an a plus 1 here, and then a 3a over here. So in the end, that's going to leave us with 4a plus 1. And then, well, we're also going to have this attached to the square root of a, and here we'll have 3a plus 3, and over there we'll have a, so in the end, that'll be 4a plus 3. So that's just from factoring stuff out. But now we can bring those inside, and here we'll have the square root of 4a plus 1 squared times a plus 1. And then here we'll have, let's see, the square root of 4a plus 3 squared times a. So of 16a cubed plus 24a squared plus 9a plus 1. So that's what we get when we multiply all of that out. And then over here, multiplying this out, we'll have the square root of 16a cubed plus 24a squared plus 9a. But now let's see what we have. We've got something plus 1 in this first term, and then we've got the something in this second term. But that means that, well, we know our a sub 3 term here. So a sub 3 will be the 16a cubed plus 24a squared plus 9a. But now let's observe that our final goal here was to show that these a1s, a2s, and a3s were all natural numbers. And let's observe that we have that so far because a is starting as a natural number. So let's maybe collect some of that information over here. And eventually we're going to try to get some formula for these a numbers. Let's observe that we have a1 is equal to a, and then we have a2 is equal to 4 times a squared plus a, and then a3 is equal to 16a cubed plus 24a squared plus 9 times a. Okay, so now what I'd like to do is start to approach this from another direction. And that other direction is to look at a number which is perhaps kind of logically connected to this x, and that would be its radical conjugate. So let's call that radical conjugate y. So in other words, y is equal to the square root of a plus 1 minus the square root of a. And I'd like to observe that that's the same thing as 1 over x, which you can see by a straightforward calculation. And now, well, now I'd like to observe that if we look at combinations of x and y, something interesting happens. So if we do x plus y, we'll get 2 times the square root of a plus 1. If we do x squared plus y squared, well, what are we going to get in that case? So recall that x squared was equal to what? Well, that was going to be equal to 2a plus 1 plus 2 times the square root of a squared plus a. And then y squared is going to be 2a plus 1 minus 2 times the square root of a squared plus a. But observe that we get some obvious cancellation here in the so-called cross terms. And we'll see that this is equal to 4 times a plus 2. In other words, it's 4 times a sub 1 plus 2. And now let's look at x cubed plus y cubed. And if you were to multiply this out, you would see that you get 3 times a plus 1 times the square root of a plus 1. And then, sorry, that should be 2 times a plus 1 times the square root of a plus 1. And then we'll also have, let's see, that'll be plus 6 times a times the square root of a plus 1. So I think even from these first couple of cases, let's observe that these odd-powered combinations of x and y will always give us something involving the square root of a plus 1. Whereas these even combinations of x and y, or powered combinations of x and y, don't. That's because the square root of a plus 1 term cancels. And let's see that happen with x to the 4th plus y to the 4th. And if you expand this out, what you'll see is you get 4 times 4a squared plus 4a plus 2. In other words, it's 4 times a sub 2 plus 2. And then if you continue this on, x to the 6 plus y to the 6, and you expand that out, you'll see that you get 4 times 16a cubed plus 24a squared plus 9a plus 2, which by our definition over here is 4 times a sub 3 plus 2. So I think maybe this leads us to say that it seems like the following is happening. And that is a sub n is equal to, let's see, x to the 2n plus y to the 2n minus 2 all over 4. Okay, so now let's maybe see what it would take to prove this and then maybe finish everything off. So in other words, we need to show that this x to the 2n plus y to the 2n minus 2 over 4 is exactly the thing that's under the radical here. And then we also need to show that it's always a natural number. And then we will have completed our task. Okay, so let's first show that this number a sub n, which is defined by these powers of x and y is exactly what lands under these radicals in just the expansion of x. And then we'll show that it's always a natural number. So here we've got a sub n, seems like it's 1/4 times x to the 2n minus 2 plus y to the 2n. But notice that means that a sub n plus 1 is equal to 1/4, and then x to the 2n plus 2 plus y to the 2n. That's because if I add 1 here, it's like adding 4 inside of this thing that's being multiplied by 1/4. And next up, let's observe that I've left a little gap here, and that's because I want to notice that this is the same thing as x to the n times y to the n. Because x times y is 1. Same thing here. This is x to the n times y to the n. But that gives us a nice factorization. Notice that means that this factors as x to the n minus y to the n quantity squared, but then our a sub n plus 1 factors as 1/4 times x to the n plus y to the n quantity squared. But now let's notice that we can take square roots here, and well, we're getting to the point where we're kind of in a good spot. So we have the square root of a sub n is equal to 1/2 times x to the n minus y to the n. And then the square root of a n plus 1 is equal to 1/2 times x to the n plus y to the n. But check it out. Now we can add both sides of this equation and we're pretty much done. So we've got a sub n plus 1 plus radical a sub n is equal to x to the n. In other words, the half x to the n's build up and the half y to the n's cancel. Okay, good. Well, what we've shown is that if a sub n is defined in this way, then yes, this a sub n is the number that ends up in the radical here in the expansion of x to the n. Now we need to show that it's always a natural number. Okay, so let's see how we'll show that this a sub n is always a natural number. So I'd like to do the following. So let's take this a sub n and we'll write it as 1/4 times x to the 2n. But notice that x to the 2n is simply the square root of a plus 1 plus the square root of a to the power 2n. And then we'll have plus 1/4 y to the 2n, but that's radical a plus 1 minus radical a to the 2n minus 1/2 from taking the quarter through to the 2. And now we're going to expand each of these using binomial expansion. So let's see, this first one will be the sum as k goes from 0 to 2n. We have 2n choose k. And then after that, we're going to have a plus 1 to the 2n minus k over 2. The over 2 is because we've got a square root there. So I can write that as n minus k over 2. And then we'll have a to the k over 2. And then we'll have 1/4, and then the sum as k goes from 0 to 2n of something similar over here, but it's going to be alternating given that we've got this minus sign built in. So let's see. We'll have a plus 1 to the n minus k by 2, and then a to the k over 2, and then from that we need to subtract 1/2. Okay, good. And then, well, let's observe that when we add those two things together, the only terms that survive are even. So that means we'll have 1/2 plus 1/2, or sorry, 1/4 plus 1/4 is 1/2. And then after re-indexing, keeping only the even terms, we have the sum as k goes from 0 to 2n. 2n choose 2k. And then after that, we're going to have a plus 1 to the n minus k and a to the k minus 1/2. So let's observe that we don't quite know that this is a natural number, but we do know that it is at least inside of z 1/2 or 1/2 z. So at most, it has a denominator of 2. That being said, I think a good strategy here would be to solve this for the big sum. So if we were to do that, we'd get the following. Notice that 2 times a sub n plus 1 is going to be equal to this sum as k goes from 0 to 2n of 2n choose 2k, and then we have a plus 1 to the n minus k, and then a to the k. And observe that under this setting, what we need is for this to be an odd number. And if that thing over there that I have underlined is an odd number, then, well, our a sub n is most definitely a natural number. So let's see if we can prove that. Okay, so like I said, we've gotten this down to needing to show that this sum is odd. So now what I'd like to do is look at this 2n choose 2k, that binomial coefficient. So by definition, that's equal to 2n factorial over 2k factorial times 2n minus 2k factorial. So that's just the definition of the binomial coefficient. But next up, what I'd like to do is use this following fact. So maybe I'll put it down here in blue. And that is that we can take 2 maybe times anything. I'll use m factorial. And we can rewrite it as 2m times 2m minus 1 times 2m minus 2, all the way down 3 times 2 times 1. But then I want to group the even terms. That would be like 2m times 2m minus 2, all the way down to 2. But then I can factor 2 out of all of those, leaving 2 to the m power times m factorial. So that's simply the even terms. And then after that, I've got the product of all of the odd terms, but that's going to be 2m minus 1 double factorial. That's simply 2m minus 1 times 2m minus 3, so on and so forth. But now I can do that in the numerator as well as the denominator here. So that's going to give me 2 to the n times n factorial times 2n minus 1 double factorial. And then in the denominator, I'll have something similar. I'll have 2 to the k, k factorial, and then 2k minus 1 double factorial. That's from this first one. And then I'll have 2 to the n minus k times n minus k factorial times, let's see, 2n minus 2k minus 1 double factorial. Okay, good. But now I'd like to observe that this double factorial is definitely odd. That's because it's a product of only odd terms. But then this one is also odd for the same reason, and this one over here is also odd. But then also we see that we get some cancellation. This 2 to the n cancels with this 2 to the k and this 2 to the n minus k. But now what I'd like to do is reduce this whole thing mod 2. But if we reduce this whole thing mod 2, the things that are odd are simply 1 mod 2. So they don't contribute to the equivalence class mod 2. So that means we can forget about all of the odd terms and see that this is congruent to n factorial over k factorial times n minus k factorial modulo 2. But now that's going to be congruent to the binomial coefficient n choose k mod 2. Because that's equal to the definition of the binomial coefficient. Okay, so now let's take this information, and by this information I mean that this binomial coefficient here, 2n choose 2k, is congruent to n choose k mod 2, and see how we can finish this off. Okay, so let's finish this thing off by showing that this object is odd. And so let's start by reducing mod 2. So if we reduce this thing mod 2, what are we going to get? Notice that should have been n from before. So we're going to have the sum as k goes from 0 to n of n choose k, and then we'll have a plus 1 to the n minus k times a to the k. Okay, good. But now I'd like to observe that we have essentially an expansion here. And this is the expansion of the following thing. We've got a plus 1 plus a raised to the n power. Notice that this is like our a plus 1 to the n minus k and our a to the k. But observe that that's exactly 2 times a plus 1 raised to the n power. But let's observe that that's most definitely odd because a was a natural number, so 2a plus 1 is odd. If you raise it to the n power, you get something that is odd. But let's see. How does that finish everything off? Well, let's make sure to see. So let's notice that we have this is congruent to 1 mod 2. But then going from the extreme left to the right, we see that 2 times a sub n is congruent to 1 mod 2. Well, recall that we already knew that a sub n was at least a half integer. Well, that means that 2a sub n is an integer. But if 2a sub n is 0, then a sub n started off as being an integer. But since everything was positive, we know that that means that a sub n is, in fact, a natural number, which was the last thing we needed to show.